I'll go hide away
No,
now.
no, no. You can you can hang around. We're happy to hear you, see you.
Yeah, I apologize for coming to the wrong
No,
room.
no.
That's what Bob said. You know, a bar chat or something like do a small talk like before the formal discussion is fine. We try to make it like flexible. You know, there's no need to be so formal.
Okay, you're up to 31. All right, I'll sneak away here like this. That way, I'm still here, but now.
All right. Yeah. We wait till 11:05 for you to start, Kong. Okay.
Am I starting? I thought you were supposed to talk. We can wait like 15 minutes or 1 hour.
I will wait. We'll wait another couple of minutes. People.
Okay.
11:05. Okay.
Whatever. You're the boss,
so to speak. Yeah. Yes, good morning, Anne.
Morning. Morning, Anne.
Okay, another half minute. Okay, so why don't we get going this morning? So today we're having a very special guest, the guy who actually organized almost all of these seminars. He did 99.9% of the work to get them going. That's Kong Tan. And there are two reasons to have Kong speak today. One is that he is graduating very soon from our group at MIT. He's going to be moving to Paris to join Jeffrey Bodenhausen and his colleagues at the École Normale, where he will be a junior professor. He'll be departing MIT in, I think, about 10 days, 2 weeks, something like that. And the other thing is, of course, the real reason is that we didn't get our act together and get it organized for another speaker today. So a couple of days ago, or maybe even yesterday, I told Kong that he had to be the speaker today. So he's going to talk about a couple of topics, 2 or 3 topics that have not really been discussed at this DNP Zoominar series. One is electron decoupling. This is a topic that some other groups, Xander Barnes, for example, has worked on extensively. He's going to also tell us about some pulse DNP experiments. And finally, the third topic, he's going to explore the recherche aspects of the spin diffusion barrier in organic free radical systems. Okay, so Kong, the virtual floor is yours. Right.
All right, thank you, Bob. I mean, that's a very, very, very nice introduction. I mean, that's perhaps like, I remember the last time that you introduced me was perhaps like when I came to your lab for a seminar 5 years ago, and then like this is perhaps the last one you introduced me here in this occasion. And you're right about the second reason is I will apologize because I have less than 24 hours to come up with a 40-minute presentation. So I apologize if my talk does not sound very fluent or if my slides are a bit crude. So just before I show my PowerPoint, I will just do like the usual thing that I've been doing like for all this series. So like of course we have a mailing list, the recording available, and then feel free to check for the Q&A of our class sessions. I copy and paste all the information onto the chat room. So feel free to look at them if you are interested. So I will now try to share my screen. And as one of the tradition here, I will try to share my screen, and I should use a green laser pointer. Oh, this is red. How do I change to laser color? It should be green. I mean, that's best Bob's favorite color. Okay, so I'm going to talk about, I mean, the title of my talk today is, as I sent out the email yesterday, is shedding light on nuclei near the spin diffusion barrier via electron decoupling. But as Bob mentioned, like I was advised I should perhaps like talk about different topics. So this is the context that I'm going to talk about today. Mostly it's all about DNP, and I will talk about spin diffusion barrier, and then like how I elucidate the nuclei near the spin diffusion barrier using electron decoupling, and then for the last few slides I will talk about pulse DNP. I mean, top DNP. So some of you have already listened to my previous talk at ENC, or maybe you have read my paper. So I will. This is relatively old. I mean, it was published like more than 1 year. I mean, it was published January last year, 2019. So I will perhaps not spend too much time on it, depending on if you are too tired. Okay. So there are several mechanisms that you can exploit to perform dynamic nuclear polarization, mainly solid effect, cross effect, or Oberhauser effect, and thermomixing. I mean, this is CWDNP, and what I show here on the right is a typical DNP field profile that you will see if you shift the microwave offset across the EPR transition, which is shown in red color, shown in red here. So if you if you set your microwave frequency of your magnetic field offset such that you satisfy either zero or double quantum condition, you get either negative or positively enhanced peak. So on the right axis here is the enhancement, and x-axis is the offset frequency. I mean, you might be surprised that why am I getting such a huge enhancement? It's about 200. And that's because like for almost all the experiments, for all the data I will be showing here are all performed at low field, which means which is 0.35 Tesla. Or if you are from the EPR community, you will immediately recognize that this is the expand frequency where I have access to a high power microwave source, which is as high as 1 kilowatt, and even for the lower power one is 10 watt, but this is good enough for me to explore a lot of pulse DNP mechanisms, and also explore many interesting physics. And bear in mind that this is done at static experiment because I use a static EPR probe, which we modify it to have the DMP capability. So you're probably so this is typical like field profile you will see everywhere. But what I did was I try, you know, when I set this up, I try to scan through a bigger range, and then surprisingly, we found that if you sweep it further enough, like far away from the resonance condition, meaning twice the Lamarck frequency away from the EPR transition, we saw a surprisingly huge peak, which you get enhanced of about 100 at plus or minus 2 the Lamarck frequency. So we were surprised, okay, where did this come from? So we looked into the literature we talked about, and we realized that this was something that was first discovered, not by us. It was first discovered by Borghini, and it was reported in 1974. And he reported this, what he called a double solid effect. It has an enhancement of 3 at extreme like conditions, 0.7 Kelvin and 2.5 Tesla. So, even though like it was reported, having seen these resonance, this DMP condition plus minus twice the Lamarck frequency, there wasn't a very clear theoretical explanation to this and what it arises and what is the transition probability. So I was interested in it. So so I tried to like come up with a theoretical reasoning of this effect. And one of the logical explanation to this is it should have, since the offset, the matching condition is at twice the Lamarck frequency, it makes sense to think that there should be at least 2 protons coupled to this electron system. So immediately we set up a 3-spin energy level diagram with 1 electron coupled to 2 nuclei. And then immediately you can see that from here, if you have a 3 flip, so flipping from alpha, alpha, alpha to beta, 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 so a triple quantum transition, you will have an offset condition of plus 2 omega naught I, and there's also a single quantum condition, alpha, beta, beta to beta, alpha, alpha. So if you match this condition, you will get a DMP. So I did the theoretical derivation, and then like this is the transition probability. So omega 1s is the Rabi frequency, microwave Rabi frequency, and B is what we call in the EPR community, we call it a pseudo-secular hyperfine interaction. I mean, which essentially comes from dipole coupling. I would use, you just have to remember, like I will use a notation. I will use an interchange notation between B or dipole coupling, but they are essentially very, very similar terms. And it's important to note that this scale is omega naught I power of 4, and this is B squared, which means that you will see from the next few slides that it has a very critical dependence on the electron nuclei distance, which I will exploit to probe the spin diffusion barrier. So that was my theory, and I wrote the DMP simulation program to confirm my theoretical thesis. So on the right-hand side here, this is the DMP simulation I performed, and then like by including or excluding the 3rd nuclei from the simulation, I'm able to show and confirm that in fact what we saw experimentally comes from a 3-spin effect, meaning 2 protons coupled to an electron, and hence we call it a 3-spin solid effect. Okay, so you might ask, what can we do with it? You know that it's a higher order effect, and you will not get an enhancement that's as high, that's as good as you would have in a 0 quantum or double quantum DMP. But I look at the theory and I thought maybe it could be used to probe the spin diffusion barrier problem, one of the very elucidating problem that has been the community has been concerned with, but we have very limited experimental data to show that it exists or to quantify the distance. So I will just have one slide here to explain what is spin diffusion barrier. So bear in mind that in DMP, it's a multi-step process. So usually you would have the electron transfer the polarization to the nearby nuclei, and then the polarization on the nearby nuclei would go to the bulk protons or bulk nuclei via the spin diffusion. And whether this spin diffusion mechanism is efficient or not, it depends on the size of the hyperfine coupling. So it cannot be too small, otherwise your DMP transfer will not be efficient, and the hyperfine cannot be too large either. Otherwise, you will experience very the spectra will become very broad, and it also will experience very extreme, very fast relaxation, thereby impeding or truncating the spin diffusion mechanism. So there's a sweet spot where the nuclei should lie so that it could still perform the DMP or spin diffusion efficiently. So so for what you see here on the right hand side here, so if this nuclei fall in the bad region, the hyperfine is too strong, they are broadening the line beyond detection and able to perform spin diffusion to the outside nuclei. So we call like this the nuclei that falls within this region. We call it like the nuclei within the spin diffusion barrier, a barrier that stops the the radical from polarizing the bulk. Okay, so what's the relevance of this to what I'm going to three-spin solid effect? So as I showed earlier, from the theoretical calculation, the probability of the transition probability is scaled with B squared. B1 is the coupling to the first nuclei, and B2 is the coupling to the second nuclei. Assuming they are about the same order of magnitude, this should scale with R to the power of -12, because like square is -6, and then the two of them power 4 nucleus, you scale with R -12. So what it says is that this is extremely sensitive to the electron nuclei distance, much more than other DMP mechanisms. So by exploiting this transition probability, I can probably probe the size of spin diffusion barrier by performing deuteration on the radical. So that's what I did. So this is the trital OXO63 that you saw in the first slide. And this is on the right hand side here, this is the structure of the trital radical, of which R here, this is for the OXO63, you have the protonated CH2 OH here, and you have good enhancement, about 200. And if I start deuterating them, meaning like if I start partially deuterating the first two, the two closest proton deuterated, then you can see that, all right, the zero or double quantum DMP, the first one here, is a bit lower. It's not too much, about 10%. But the one at the three-spin effect, it becomes attenuated by a factor of 250. So this is a huge decrease. But nevertheless, we do not have a radical that is completely deuterated. So we turn our attention to another radical, which is Finland trital, and then of which the R group here is just CH3 is a methyl group. Then you get almost roughly 10 to 20% DMP enhancement on the normal solid effect. But then like for the three-spin solid effect, it's about the same. But the interesting things start, the most interesting result comes on the next part, when we start to deuterate this Finland trital, meaning CH3 to become CD3. And even though like the solid effect condition is, the enhancement is roughly the same, but it completely quenched the three-spin solid effect DMP from 100 to almost, I don't know, 5 or almost nothing, almost 0. So what it implies here is that the intramolecular protons, meaning the protons on the trital radicals, they are important in mediating the spin diffusion to the bulk. So if you start deuterating these guys, the three-spin effect, TSSE DMP will not have happened. And this indirectly proves that these protons on the radical, they are responsible, they lie outside the spin diffusion barrier, and they are important in polarizing the bulk nuclei. So based on this reasoning, and also like if you read the paper, I have other scientific data to support this idea as well, I'm able to show that these nuclei, intramolecular protons on the radical, they are outside the spin diffusion barrier. And I say that this is about less than 6 angstroms. And apart from that, I also use the custom-built simulation program to prove my point. So in here, I have 3 systems, and I just change the electron nuclei distance from 4 angstrom to 4.6 to 5.5. The take-home message from here is that even though I changed the distance by merely 0.6 or 1.5 angstrom. This is a very small change in distance. And then it does not affect, it has minimal effect on the normal solid effect, but it has a drastic effect on the three-spin solid effect mechanism. So thereby showing that proving or indirectly showing that the transition probability is indeed very, very sensitive to the distance because of the R-12 dependence here. Okay. So apart from, so we more or less figure out one of the transfer polarization pathway from the radical to the bulk, but then we try to map out the whole story of how the polarization transfer happens. So apart from doing that, I also did an endo experiment. So this is, if you know about EPR, you're probably familiar with this, but I will just I will try to explain it qualitative here. So this is the pulse program for the pulse sequence for the endo sequence. What you would get if you have a perfect or ideal system is that for the MEMS endo spectrum is that you will see a peg doublet like this, and then from that, if you see a peg doublet like this, you can assign the hyperfine interaction. Thereby, you can try to probe the size of the hyperfine interaction or dipole coupling. Yeah, so I did this experiment. So first, for the deuterated Finland triidal in the DMP juice, you don't see any feature here because there are too many residual protons coupled to the electron. So this is not too interesting. But then when I repeated the experiment in protonated glycerol with D2O or H2O, more or less the same line width. Okay. What this data implies is that the glycerol is very, very close. The radical is actually shielded by the glycerol, or the glycerol is is sticky and it probably sticks or snuggles up to the radical, and it's probably the first molecule to be polarized before the transfer for polarization from before transferring to the bulk. So that's what I say here. The glycerol snuggles up to the triidal and it's probably the first solvent molecule to be polarized compared to H2O or the molecule of interest like your biomolecules, etc. So by stitching all these stories together, I'm proposing that the polarization transfer pathway in a DMP mechanism is that first you have the polarization from electron to the protons, protons sitting on the triidal, and then the triidal protons, the polarization of the triidal protons will go to the glycerol protons via spin diffusion, and then at last it will go to the bulk. So I made a video here to explain what I just told you. So the purple sphere is the red barrier, and then you have the initial polarization from electron spin, and probably it goes to the intramolecular protons first on the triidal, then it goes first to the glycerol, and then it transfers to the bulk, which could be glycerol, water via spin diffusion. So so that's what this is like so whatever I showed here was published in the Science Advances paper that I published last year. So you can look it up if you're interested. So after that, after I presented the data in ENC, and then I talked to several people. I mean, most importantly, I talked to one of my colleagues and also Daniel Lee from Grenoble, and I got an idea that okay, I want to really nail down this hypothesis, because like whatever I showed here, even though it was nice, it was like nice experiment data, but I thought maybe I could really nail down, come up with a very, very solid experiment data to support my hypothesis. So I thought if these triidal protons are indeed lying outside the spin diffusion barrier, I should be able to directly observe them with NMR observations, right? I mean, it makes sense, right? If first you have to be able to observe them, meaning that they are not broadened beyond detection before. I mean, this is an important criteria for it to perform spin diffusion efficiently. So I thought, okay, maybe I can try to observe them. And I was not confident that I would be able to observe them because like even though I say they are outside the spin diffusion barrier, there could be still broadened somehow by the hyperfine interaction because like they're 6 angstrom, they're still few hundred of kilohertz. Then I thought maybe I can somehow quench the hyperfine interaction or the spin diffusion barrier to a smaller scale and via electron decoupling. I mean, making the intensity higher, which could help me in the NMR detection because, you know, the DMP sample that I prepare, you know, it has only a few millimolar of radicals, and then I'm observing very few number of protons. And I might not have a very good sensitivity and anything could help. So that's what I did. And one of the advantages of working at low field is that I have an array of microwave instrumentation available. So what I use here is an L-dot channel. So I have 2 microwave sources and I can change the frequency almost. I have 2 microwave sources that I can irradiate them at different frequencies and I can manipulate them in whatever way I like. So this is good because I can polarize them at the DMP condition and I can electron decouple them at another position. So this is what I did. And in fact, I did see an improved intensity using the electron decoupling technique. So as Bob mentioned, I'm not the first person to do this. Alexander Barnes, who is now at ETH, he did a beautiful work and he was the first person to show this effect. So, so this is the experimental data. What I showed here on the blue, this is the EPR line on Tridal. And then I did, the experiment clearly show an improvement of about 80% of the NMR intensity if I put the microwave frequency irradiating exactly at the EPR transition. This is also in good agreement with what Xander showed. Okay, so I have a huge huge sensitivity. I wouldn't say enhancement now, but I would say like higher intensity. And this is the 1D slide of the electron decoupling on and off. All right, so this is good. I'm able to see these protons, but I was a bit concerned about that, even though I performed these experiments on a sample with almost, I thought it was close to perfect deuteration because like it was deuterated DMSO, D2O, and I put a bit of D8 deuterated glycerol. But then I realized that my results were not. I wasn't sure that I'm detecting the protons from the Tridal radical, or I'm seeing the residual protons in the solvent. So so the question is how can I make sure that I'm only seeing the organic radicals protons? So in order to do that, so I would like to repeat the experiment for doing the same thing again. So repeat the experiment once for the proton and then repeat it again for the deuterated Finland. I expect the one with the deuterated Finland to show nothing. It should not give any proton spectrum at all. And I'm using highly deuterated solvent, so 99.96%, which Cambridge isotope advertised as almost 100% deuteration. But there's actually this is a challenging thing to this is challenging to prepare the sample. Firstly, because you want to make sure that you pack everything inside a glove box to minimize contamination. And then the second problem is that if you switch to a Finland Tridal aggregates very readily, especially in non-polar solvents like this. So ideally, you would like to you like to keep it frozen and most of the time, and you also want to flame seal it. So and then flame sealing quartz EPR cube is not trivial. You need to have a flame torch that can go as high as 2000 degrees Celsius. So the idea is that you need to prepare in a glove box. Once you take it out from the glove box, you have to flame seal it very quickly and carefully. I mean, so I had a lot of trouble doing this, and luckily I have my colleague CB from my postdoc in my group to help me to do this. So in order to do this, first I 3D print an adapter so that I can connect the 4-way tap to the EPR tube here. I have an O-ring here, and like it was incredible because like we make this ourselves, and the 3D printing was nice, and it's actually better than I expected. I tested it; it was able to hold a 10 to minus 2 millibar vacuum and it's lip tight. And then with the 4-way tap here, I have 2 of them. And with one go, I can prepare 4 samples at the same time, which is good because there's a lot of effort to do this. So we did this, and this is the result. So on the proton Finland trido, okay, I have good like proton NMR signal, and this could imply that what I'm seeing here is perhaps the protons from the trido radical, nothing from Northern. And then when I switch to dual-traded Finland, it's not exactly nothing. There's still something in there. I mean, there are still some residual protons in it, even though it has a much lower intensity. So I was surprised where did it come from? But then like when I checked when I look up to the specification sheet on Cambridge isotope, the dual-traded solvent that I use, it only has a chemical purity of 99.5%. And I did of course, I don't know what kind of impurities they have in the sample, and it varies from batches to batches. But assuming that it's the same as assuming like the 0.5% impurity comes from protonated DMSO, it could still give it could still give a significant proton background to my DMP experiments. But nevertheless, since I prepare both samples using the same solvents, and then I've characterized the DMP efficiency of these 2 radicals before, and having a NMR signal intensity ratio of about 5 to 1.5 or 2, I think I'm somehow convinced that whatever I observed, the extra intensity I observed here from the proton Finland trido sample comes from the protons on the trido radical. So thereby giving them a direct proof that these protons should be outside the spin diffusion barrier. Okay, of course even though I was like more or less convinced, but I still want to push for it. I still want to get a better answer. Try to support my idea. If you're not 100% convinced, one idea I thought I could try was to actually turn my attention to fluorinated trido. So for fluorinated trido, it's good because like doing like 19F DMP, because 19F has a very high gyro magnetic ratio, it's 94% of proton. It has similar hyperfine coupling and also dipole couplings, because spin diffusion it is proportional to gamma squared. So in principle, the spin diffusion barrier story will still hold. And of course, it has the fluorinated trido here. It has very narrow line width, and in principle, it should not be too different from the other tridos that I've experimented before. And it's nice that so Benoit from West Virginia University, like he gave me these samples. So this is like he did a great job. So the next step would be try to do 19F DMP. And here, of course, like whatever I've been doing in the past was to look at the proton DMP. But then like to do a 19F DMP, I need to change my probe slightly. This is okay. It's very easy, because like at low field, the 19F Raman frequency is only like 800 kilohertz away from the proton one. So I have to modify the single channel, the resonance circuit here. And of course, I don't want to make a different probe, and I want to have the flexibility of changing between proton and 19F. So I bought a very large a variable capacitor here. You can buy this from Amazon, and this is nice because it has a very, very huge tuning range from 25 to 400 picofarad, and it allows me to shift between have a resonance between 12 to 16 megahertz, so 4 megahertz tuning range. With, if you look at the vector analyzer, I can get negative 40 dB, which is on the S11 parameter, which is very good. So having the radicals and the hardware ready, I did this, and of course now on the 19F DMP, I do get a 19F signal, and then now I don't have to worry about 19F because my solvent should be 19F free, and I don't see anything on the OXO63. So that supports the idea that whatever I see on the dual-traded, on the fluorinated trido should come from the fluorine atoms on the trido radical. So this fluorines are definitely outside the spin diffusion barrier. So this somehow, I mean, I'm almost like 100% convinced about the data, and so this completes the hypothesis or the story. So direct detection on 19F on radical, it confirms that they are outside the spin diffusion barrier, and so the next thing that I have to do is to quantify this distance, and then Michael Mardini, a grad student in my group, to help me with the DFT calculations, so that we can say whether it's like 6 or 7 angstrom away from the radical. And apart from doing that, I mean, since I have the radical already, I also did electron decoupling, and here the story is almost the same. When you have the microwave frequency irradiating the EPR transition, you have the signal almost double. I mean, like, I don't know, so 0.28 to 50, 52 or 53. So it's about 80% to almost double. So this is very, very similar to what I observed before. Okay. So, and then the next thing is, okay, you might ask, what can we do with it? I mean, with this electron decoupling, and then you're observing the nuclei near this spin diffusion barrier, what can you do with it? So, I mean, one of the very important questions is that once you model these things, it's actually important to know this near radical nuclei, because they might not have the same T1 and T2, and knowing them would help you to improve your radical design. So that's the motivation. That's my one motivation. So I measure the T1 of these protons on the tritol, and then it's about 11 seconds for the T1, and for the T2, I did with the electron decoupling on off. And when I saw this, I was very surprised, and obviously I didn't know what to do, because it's very, very contradictory. In principle, if you imagine, you have imagined that the T2 would be longer if you do decoupling, right? But this is the opposite. The T2 actually becomes smaller, becomes shorter when you do electron decoupling. So how could that be? Shorter T2 with electron decoupling, you see the bi-exponential decay, and you might ask, what is inside the Pandora box? Should we look inside it? So bear in mind that I'm doing this at static condition. So this is a solid echo. Of course, like what happens here on the x-axis is that I change the echo time here. If you take a trace at these two data points, one at 10 microseconds and the other one at 50 or 55 microseconds, of course the intensity will be different. But if you normalize them with respect to the maximum ratio, you can see that they do not have the same line shape. In fact, it looks like it's a superposition of multiple NMR peaks. So, in fact, what the story tells us is that perhaps whatever I see here cannot be simply characterized by a single exponential. There could be multiple components, and whatever I have here is a mixture of superposition of broad and narrow peaks, meaning that they are not necessarily homogeneously coupled together. So, you know, these protons, this is a nice story to tell you that those nuclei near the radical, they do not behave exactly the same way as the bulk, and there's a smooth transition, and definitely a lot of analysis has to be done to understand these close by protons, because which will elucidate some information that you could use to improve the design of the radicals. And okay, and it's also like when I did this around the same time, it was also nice to see the literature, to look at the literature and look at Janus' paper. He also reported a very similar phenomenon. He also says that, oh, it actually showed a 17% increase in line width when you use a short DMP time. So broader line with electron decoupling on. So it's nice to see that I'm not the only person to observe this effect. In fact, like Janus also showed that he also observed a similar effect. So this is good. I mean, our data are somehow in agreement with each other. Of course, like the context is slightly different. He's probing at the 13C of, if I'm not mistaken, is proline or urea. But whereas for me, I'm interested in the protons on the tridal radical. Okay. The next thing is that I was also interested in using the low field static DMP to probe some of the to probe some materials. So we have a collaboration from a group at MIT who specialize in this meta-organic framework, Mercer, Dinker, and also Looming. Looming was the one who made all this MOF. So this is the MOF with magnesium in for the metals M, and then like for the organic linker, he has the hexahydroxy triphenyline as the organic linker linking the magnesium atoms together. And then these organic linkers, they have several oxidation states, and they are paramagnetic in nature. So this is a sample in which you have endogenous radical embedded in it. You do not need to add extra polarizing agents or whatsoever, like trital or biradicals. So he was interested. They were interested in this MOF because like he has some significant electric conductivity, and it could have applications in semiconductors or quantum information. So the first thing what we did was to characterize the EPR line. So so this is the spectrum taken by Looming. It has a very narrow line width. So if you are not familiar with this is the EPR spectrum taken with the derivative spectrum. So this is not a field profile. It had the line width only like 17 megahertz broad, and then like the radical concentration is about 4 millimolar. Is a lot lower than what we expected. We expected it to be 400, but we do not know why it's only 4 millimolar. There's still a lot of like work has to be done to understand this sample. But when I look at this spectra, yes, narrow line, and also like in a favorable DMP conditions, concentration compared to the trital sample that I've been working on. So I thought maybe I could try to do some DMP on it, and then like it worked perfectly. So I just did a DMP, and then on this endogenous radical, I have a DMP enhancement of 90, which is quite good. And then it exhibits a typical mono radical feature, just a solid effect separated by twice the Larmor frequency. It doesn't have anything like overhousing effect or cross effect or thermomixing DMP feature. So this is good. In addition to that, I also did electron decoupling. So like on the left here, the effect is not that great. I mean, like I only saw an improvement of 4% for the unactivated sample. We just got we got an activated sample from Looming like recently, and I've not shown it here because I just got the data like last week. It shows an improvement of 11%. When I say activated, I meant that the sample will be at temperatures which you remove the solvents and water molecules, thereby assure that whatever you observe here would the proton signal you see would come from the organic part. And bear in mind that there's only one kind of proton nuclei in this sample. So it's nice that so this is good because like I don't have resolution at low field. And why is it less efficient compared to trital? I do not know the full story. Probably it has the line width a bit larger, and probably the hyperfine is a bit bigger relative to trital. And also we do not know the full story about we have not fully characterized the radical yet. I mean, we expect it to 400 millimolar. Why is it only 4 millimolar? I do not know. Where did the 99% go? Or maybe it didn't exceed at all. So these are some of the open questions that we are still trying to answer. It's 11:43. I think I can perhaps go on for 10 minutes. I don't want to bore you guys. So that's the part for the spin diffusion barrier and electron decoupling. I'll spend maybe like the next 5 or 10 minutes to talk about top DMP. This is relatively over. So why are we interested in pulse DMP? Because as you know, for CWDMP, continuous wave microwave irradiation, and one of the most exploited effect is the cross effect. It has a lower enhancement at higher B0 field. So this is the data for MUPO. If you go from 211 to 600 to 800, the enhancement keeps decreasing. And I know like this is nowadays, like amyloid is not the ideal polarizing agent for high field DMP anymore. A lot of beautiful work have come out from Oliver Vary, Marcel, and also like from Snorri, Iceland, and they've tried to come up with a better and optimized polarizing agent at higher fields. But in general, this trend is more or less still something like impeding the perhaps the prospect of doing DMP at who knows at 1.2 gigas or even higher magnitude. So we are interested in having DMP mechanism or radicals that should in principle give a field independent enhancement at all fields. That would be the ideal scenario, right? So that's why this is one of the areas that we are trying to develop. And there's a gold standard for pulse DMP mechanism, which is called novel. And the principle is very similar to Hartman-Hunt CP, where you try to match the Rabi frequency, the Rabi field here, the microwave power, to the proton NAMA frequency. And again, this is at low field, 0.25 Tesla, where the Rabi field, the proton is only 50 megahertz. Of course, with the Rabi field, you can do that like easily with 50 megahertz, and this is on diphenyl nitroxide, and then you get like perhaps like about enhancement of 100 or 200 or so. And in principle, from a theory, it says that it should have field independent enhancement factor. So this would be very good for us to use it in future. But then one of the disadvantages is that it requires a very high power. Imagine that if you want to do it at 9.4 Tesla, you need to have a Rabi frequency as high as 400 megahertz. And then like, yeah, so if you do a calculation, assuming that you have a high Q resonator, you will still probably need a high power source at high power microwave source at 1 kilowatt. Whereas the gyrotron nowadays, like at max, you probably get like 50 watt or maybe like optimized, I don't know, maybe 50 or 100 watt. Still 1 kilowatt is still far from what we can reach. So I was interested in finding out if there is if there's a low power alternative, not native to it. So when I look at the DMP theory, so it actually the theory of DMP in my perception, I think is mathematically similar to magic angle spinning. So if you look at magic angle spinning, A here is a space tensor that characterizes the spin interactions. If you do magic angle spinning at the spin at the frequency of omega r, of course it will get modulated with either 1 or twice the omega RT. If you integrate it, then it becomes 0, right? So this is how magic angle spinning works, how it gives you the high resolution spectrum. But then in DMP, it's very, very similar. You have a pseudo-secular hyperfine interaction. IX term here, that's why it's called pseudo-secular. And it's just a manifest, it's a parameter that depends on dipole coupling. Under the proton Lamar frequency, this term, the IX term here, it will get modulated. If you integrate it, it will become 0 as well. So I thought, wow, so in magic angle spinning, you do recoupling, you interfere with the integration regime to introduce dipole coupling to transfer polarization, right? Then I thought, okay, being mathematically similar, could I do something very similar in DMP? Put a pulsar somewhere close to Lamar period instead of the rotor period to try to reintroduce this interaction back to do a polarization transfer. Could I do that? So, so in order to maybe like you are not, maybe I've not explained things very well, so I just did a simulation to explain this idea. So in this simulation, I only have 3 terms here. Actually, there are only 2 terms, so I only have like Lamar frequency and B here. So if this is the simulated EPR spectrum, what you can see here is a Lamar frequency 10 megahertz and B of 10 megahertz. Then you will see there's a spin hit transition or sideband. This is known in EPR literature. And if you start increasing the Lamar frequency from 10 to 50 megahertz, you'll see that the center band increases in intensity. Then the sideband it becomes further away and becomes lower in magnitude. And if you keep on increasing it to 30 megahertz, it becomes even lower on the sideband intensity. You might not be able to see it very well, so I blew it up for you. So indeed, it becomes further away and lower in magnitude. if this rings a bell to you, if you are solid state NMR spectroscopist, you say, wow, this is like magic angle spinning sideband, right? Exactly. That's what I thought. So it's very mathematically similar. So that motivates me to think about doing Larmor period synchronized microwave pulses, meaning putting one of the simplest pulse sequence ever. Just put a pulse and then a delay and then just cycle it. So this is like Dante and RFDR or respiration or CPMG or whatever you call it. It's just as simple as that. So I tried that, and of course, like being like you have to optimize the tau and the pulse length and the delays. That's why we call it a time optimized pulse DMP, top DMP. So again, I'm showing you here. This is just a normal solid effect DMP with CW. But then if you start chopping up these pulses, you introduce a delay in between, then you start seeing a very interesting looking field profile where you have a double quantum and zero quantum DMP interleaving, right? Depending on what offset frequency that you look at. So I look at this. Wow, this is something that nobody has observed before. So I thought like, okay, this idea it seems to work, but can I now explain the DMP field profile? Before I do that, I thought sticking to the idea of NMR recoupling in solid magic angle spinning experiments. You know that in RFDR you have to somehow keep the rotor period constant. You know, like so it's rotor synchronous with respect to the rotor period. So I thought maybe I do the 2D experiment and the enhancement should be constant with respect to the pulse length plus the delay, fixed tau P and D. So that's what I did. So this is the 2D contour plot on which the y-axis here, I changed the pulse length. On the x-axis, I changed the delay. Indeed, you see that there's somehow a constant enhancement factor along the diagonal where you have a fixed pulse length and a delay. And in effect, so that's why we call it you need to time optimize these things, and they are and of course, like this is something that was not observed before, and now I'm confident that we perhaps need a new DMP theory to explain this phenomenon, to explain this pulse DMP effect. So that's what I did in the next slide. So using the custom built DMP simulation program that I built, and then with incorporation of relaxation effect, I'm able to reproduce like very, very well what I observed experimentally. Some is, you know, I was surprised. I thought it's too good to be true. And that's good because numerical simulation shows that this is indeed a true effect. And the next thing is that how can I explain this resonance condition? So I resort to Fouquet theory. So that's what my PhD thesis was about, looking a lot on the Fouquet theory. So there are a lot of resonance. There are a lot of like frequencies here. I mean, omega. So we say that if you can match this resonance condition, then you get a DMP effect. So omega m here. So this is the modulation frequency. So this is the inverse of the period here, and then effective EFF here is the effective field, which is a function of the offset, and Rabi field, pulse and delay. It's a complicated equation which you can find in my publication. So indeed, I first plotted this resonance condition. If this is matched, then you will see a DMP. So in fact, so if you see here, the blue line, horizontal line, is the Larmor frequency. Whenever this line matches either the black or the red, you have a DMP effect. So indeed, so here you see that there's a good DMP enhancement here, and also here, whenever it matches, you always get an enhancement, a good enhancement. All right. So that's good. I'm using this Fouquet theory by plotting all the resonance conditions. I'm able to show the position of this. I'm able to predict all the double quantum or zero quantum enhancements experimentally on both experiment and simulation. And then, but okay, it only shows me the position. It does not tell me how good it is. In order to characterize the efficiency, I need to calculate the scaling factor. So this was also done using the Foucault theory. This is pure calculation. You know, you don't need to put a spin system. So the square marker here I put is in fact the scaling factor between double quantum and zero quantum contribution. If the contribution here is positive and small, you will expect in the experimental data a small and positive enhancement. Indeed, I saw a small positive enhancement. And then if it is negative and large, then you also on the scaling factor you also see a large negative enhancement on the enhancement. So it's amazing, right? Because like there are also some points that you also zero and then you don't see any enhancement. So with this numerical simulations and also the theoretical reasonings using Foucault theory, we are 100% sure that whatever I see here is a new phenomenon, it's a new DMP effect, and it's nice to see that law of physics is the same whether you do magic angle spinning NMR or DMP. I mean, the interaction frame transformation, it doesn't care. So it's nice to see that I'm able to take all this knowledge that we already known about magic angle spinning solid state NMR and apply it on DMP. This opens up a whole new avenue of how we can do DMP or EPR in the future with this pulse technique. Imagine you can do redo or I don't know, pain or par or anything else. Yeah, so I think it's a very exciting from theoretical perspective. Okay, so you might ask, okay, how would it behave at higher fields? Would it still hold? So in fact, I went to Brooklyn and I repeated experiments at 1.2 Tesla. So it's about 3 times the magnetic field. In fact, I still see an enhancement that's okay. I should quickly read out. So I still see an enhancement almost 200, which is good because previously I also saw an enhancement of 200. And of course, we do not have the instrumentation available to perform it at 800 megahertz, but then I did a simulation nevertheless. And of course, in theory, in numerical simulation on the right here, I would still be able to get field independent enhancement factor. And this is not a surprise because that was expected from the Foucault theory, and also this is also what you expect from first order recoupling in solid state magic angle spinning NMR, because you don't expect the CP efficiency to change whether you do it 400, 600, 800, or 1.2, right? So I think this has a huge prospect for us to advance to high field DMP in the future, of course not near future. So my work here was, of course, it was like it has some attracted some attention, so some need reported it, and of course, so LV shading for on the future of DMP. So where are we heading? So I plotted a timeline of the development of DMP here. The DMP was first discovered by Overhauser, Schlichter, and Carver on a lithium DMP. Everyone knows about this. And in the 1980s, several groups, there were 3 groups. So it was Giannoni, Robert Wien, and Schaefer. They built the first MS DMP instrumentation. And here at MIT, Bob Griffin and Temkin, they used a gyrotron device to perform, they built a gyrotron to perform high field DMP. And then in 2000, then cross-effect barreticle was invented. And then in parallel to that, dissolution DMP was also invented, which you can use for clinical imaging now. So the question is, where is DMP heading now, or in 2020s, or in the next 10 years? I also show like a diagram here. So this is how the telecommunication like advances in the past 20 or 30 years. So it actually has some relation to this with the 5G or 6G becoming available, because we actually benefited from the microwave technology. So we say, at least like we think in here, that perhaps in the next 10 or 20 or maybe like more number of years, pulse DMP could be the possible future of how we perform NMR. Okay, so perhaps like Bob has presented this in many different occasions, and a lot of people also have doubt. I mean, like, or maybe people are curious how to progress. So I would say that this is the pulse DMP instrument at 250 gigahertz that's being assembled here at MIT, and we have all the components ready that is ready to be assembled. So first we have the probe, DMP probe, heat exchanger, and waveguide. Everything was, this was old. This was already built. The probe there is ready to go since 2003, and then the gyro amplifier is also built in 2013. And then Emilio Nani, the person, and then he measured it. You have a 40 dB gain, a device gain on the amplification. But then at that time, back in 2013, the solid state source that you had that was available in the market does not have too much power. So a 40 dB gain on a microwatt or 1 milliwatt sample does not make a lot of sense. But then recently, VDI, the company, they made a huge breakthrough. They are able to make this relatively high power AMC or VDI source that can currently output 250 milliwatt, and I think they're still trying to push it to 500 milliwatt or even higher power. And if you look at the other products made for the same company, the power available at today's scale is an order of magnitude higher than what they had 10 years ago. So we have now all the basic components ready, and it's now ready to be assembled here at MIT. And we look forward to, it's perhaps unrelated to me anymore because I will not be doing this, but we look forward to the first and working gyro DMP amplifier in the world. Maybe, of course, I'm sure that people will ask about this, and Bob will be here to tell you all the progress. So thank you for listening to my very, very long talk. Initially I want to prepare only a 20-minute talk, and then Bob told me that I should talk longer. I have no choice because I'm still being paid by him. But anyway, I'm still very grateful that Bob has been hosting me here at this wonderful place, MIT, at the back of my backdrop. And it's a wonderful time being spent here. And all this work here, I couldn't list all the members here because I could have, but these people that my group members have helped me a lot. And then I also want to acknowledge Jan, Henrik, and also Benoit for sending the radicals to me, Mercia and Luming for the morph sample, and of course Ralph Weber for hosting me for some of the DMP experiments I queued up. And lastly, Bob has said I will be moving to Paris in 2 weeks or 10 days time. So I'm looking forward to go to Paris, and then I have a postdoc position available. And you probably realize that I'm doing exotic stuff. So if you are interested in exploring exotic DMP or fundamental physics question with me, so feel free to write to me, and we are looking forward to do great science together. So thank you very much, and that's the end of my presentation, and I'm happy to take questions. And of course, Bob will help me with some of the questions. Right, Bob? Are you still there?
So there are a number of questions already from the audience. I think we have 11 so far. Let's start out with Bjorn Kozelius. He has 2 of them.
Oh.
And he says electron decoupling should modulate the spin diffusion barrier. What happens to the proton or F19 detection without electron decoupling? And he also wants to know, he also states, while the ability to detect nuclei within MR might be an indication that they are outside the spin diffusion barrier, it is not clear proof from my point of view. Could you please comment on this? Okay, so that's the first question.
Yeah. Okay, great. So on the first question, electron decoupling should modulate the spin diffusion barrier. Indeed, you're right. When I think about this, because I come from a solid state NMR background, it's really when you try to decouple carbon from the photons, if you have the RF or microwave ability to control these couplings, in my dream, I hope in the next 20 or 30 years, you will be able to turn on and off these couplings just like what you do in solid state NMR. You can do decoupling or recoupling, and you can manipulate these things at your view. I think this would be the perfect scenario. And yeah, indeed, it should. I think with how you strip it, or by considering the microwave power, you can quench the hyperline effect, in my opinion. And what happens to proton or 90F detection without that? So because the nuclei that I look at, they are weakly coupled. So if you do the end-door, they are this only the hyperfine interaction is only order of maybe 100 kilohertz or 1 or 200 kilohertz. So you can still see them, but then like it will become less sensitive. And of course, I'm working with very, very low concentration of protons, of radicals, and I have very few protons of 19F available. You can still see them, but then like they will be broader, and then like it will be less sensitive. Well, okay, and then on the question about the spin diffusion barrier, it's not a clear proof from exactly. So if you okay, there are a few things. I mean, beyond you probably know from my good friend Johannes Wittmann, my old-time colleague in APR. If you want to know know fully about the capability to do spin diffusion barrier, to perform the spin diffusion efficiency, it depends on the zero quantum line width. So if you look at the famous Kubo or McDowell description, so there are a few things. So first of all, you're indeed right. So this is only like one of the, I would say one of the first steps. First, I would say like the criteria is that there should not, the line width should not be too broad. If it's too broad, then the zero quantum line overlap will be very small, and that is definitely bad for spin diffusion. And the other thing is that, as I already showed, it's important to measure the T1. If the T1 is too short, then of course, then it could quench the spin diffusion effect. So I think in my perspective, there are two things: spectral overlap, and then of course, if you can see them, if you measure the line width, if they are not too broad, then this is the first point, and the second point is the relaxation data. And in fact, since I'm able to see this NMR directly, and then if I can go to higher field, I can, and then also I showed that there are different components. Perhaps in the future, I could perhaps do a 2D NMR on this, and maybe I can see some cross peaks. Then you could be a stronger proof, in my opinion, to see how this to measure the spin diffusion constant, to measure how it polarizes to the bulk. Yeah, but this is this is the tool that I have that's available to me at this moment. I hope you are somehow convinced at this level. Yep.
Okay, so Jeffrey, Jeffrey wants to know Bodenhausen. He says NMR lines can get broader when electrons are saturated. They get narrower when the electrons fall into their ground state. Bjorn et al. Have shown that for T1 rho. And then there are a couple of comments about that comment. Fred Mintic says that depends on the electron polarization here at 0.3 Tesla, so it may only explain partially the observation. And Nino Willie says, I also think the T1 rho effect was at dissolution DNP conditions, nearly full electron polarization. All right, so you have a reply.
Yeah, Bob, you want to say something?
No, you go ahead. All right,
No, I mean, like, this is yeah. I mean, thanks for the comment. To be honest, I have not looked into Bonnet's paper, but I will look into it. But I mean, like, I mean, the Fred and also Nino also commented on it. Like this, I have to admit that I do not know enough to comment on this. But I will look into it, and also I should say that all our experiments are done at 80 Kelvin, and then and also, like, if I'm not mistaken, I think there's a clear distinction between observing the bulk NMR and the nuclei that's very close to the radical. In fact, they should. I think they do not behave the same because they're close to the radicals. They have experienced hyperfine inflection of few hundred kilohertz, and they are almost like heteronuclei, somehow heteronuclei. But but in fact, I think I will. This is something that I hope to do in the future, and just like what I said, do a 2D and try to analyze how similar are these near electron nuclei. How similar are they to the bulk? Because I don't think they are the same.
Okay, Fred Mintic has 3 questions. Why the triple quantum are broader in the OX63 experiment versus simulations? And what are the duration of the RF pulses? And what was the temperature for the 11-second decay time? And what is the expected hyperfine coupling? So some, yeah.
All right, thanks, Fred. Thanks for your thanks for listening. Yeah, these are extremely good questions. Honestly, I do not have the full answer to why the triple quantum are broader in an experiment versus simulation. That's also I also thought about it for a long time. Also, like the reviewer also asked me the same question, but I think like because like from the very crude DMP program that I wrote is, as you know, it's a Liouville space, and then like so if I include 3 spins in it's equivalent to 6 spins in the Hilbert space, so it becomes like very slow. And I think one of the main reasons is that I've not included enough number of protons in my simulation. I think that if I include, I don't know, 10 or 20 protons, I could make the process the effect a bit broader. And the duration of the IF pulse, okay, because like we really optimized the matching box, as I said, it's a minus 40 dB on the S11 parameter. So I was able to get a 90-degree pulse will only take maybe about 2 microseconds with 100 watt or 2 watt. So if I push for a kilowatt, I can get it less than a microsecond, but I don't want to do that. It's good enough. The temperature of the 11 seconds decay. So everything I've done, I've done was performed at 80 Kelvin. And what is the expected hyperfine coupling? I think like Mike Bowman from Alabama is an expert on this, and he has measured all these hyperfine interactions, and you can look into this paper. Whether it's temperature dependent and fluctuation, I do not know, but I measured the T1 and the T2.
Okay, an anonymous attendee wants to know, will the top DNP, these resonance conditions change under magic angle spinning?
This is a very good question. In fact, this is something that that we have been working on a simulation. If you spin slow, it should not affect it. That's our answer. I mean, of course, if you limited conditions are in nanosecond or picosecond pulses, if you spin like 1 or 10 kilohertz, it's nothing. But the interesting question comes what happens if you spin faster? You know, a lot of people have been trying to push the MS frequency to beyond 100 kilohertz. If you spin 500 kilohertz, where is about the same order of magnitude as hyperfine interaction? I think that's the regime where a lot of interesting physics could really come into play.
To appear, yeah.
Yeah, rotor synchronized microwave pulses.
Yeah. Okay, Quentin wants to know, you talk about electron nuclear distances of 6 angstroms. How do you take the angular dependence of the hyperfine interaction into account?
Great question. In principle, when, of course, I'm not the first person to put up the idea of spin diffusion barrier. It was like, I think it was, if I'm not mistaken, and then of course, it's orientation dependent. Of course, this rank to dipole coupling is a rank to tensor. And then of course, if you have the electron hyperfine interaction aligned along the magic angle, then it should be 0, right? So it has some angular dependence. In fact, what we should do is actually calculate the powder average of it. But then like what we use here is just a simple sphere model. We just assume that it's a sphere, and then like we just look at roughly the powder average size. Of course, there's no clear boundary. It's also like Euler angle is also orientation dependent. So in fact, like what I'm doing here, I only like model into the simulations. I assume a powder average sample.
All right, and Nino Willie says several millimolars are quite a lot from an EPR point of view. Could electron-electron couplings influence the proton relaxation under electron decoupling, similar to the self-decoupling effect in heteronuclear decoupling?
Oh, great question. Several millimolar are quite a lot from an EPR point of view, but it's not a lot from an DMP point of view. Could the electron couplings, if I'm not mistaken, I think like for deer, I think for few millimolar, I don't remember, was it I have a table somewhere. I don't remember, was it a few hundred kilohertz or something like that. I don't know. But I think in fact it could it could affect the proton relaxation, but I don't think it will affect too much because you will still have 6 angstrom is still quite short compared to a few nanometers inter-electron distance in a 5 millimolar sound, I guess. As similar to the self-decoupling effect in particular decoupling. I obviously I do not know, but if I think like because I'm working on Tridal, I have a very narrow line radical, and then like I have a strong Rabi field. I think if I optimize it, it can be 5 megahertz. So I think I'm saturating all the EPR schemes. I mean, like almost all but all. But this is yeah, I mean you are perhaps a better person to know this answer. I mean whether there's a crosstalk between the electrons, whether you can do dear, maybe I don't know. But of course, at high field DMP, when you do, which usually you use 20 millimolar, or sometimes even you use 40 millimolar, um, electron couplings are indeed quite important. But I've not looked into that yet.
Okay, so Jeffrey wants to wants to be reminded how much microwave power you need to observe a 3-spin solid effect.
All right, great. So I'm using 10 watt. So for a Booker EPM machine, so that's MPEX 10 watt, and then I measure the Rabi frequency. If it's overcoupled, it's about 2 megahertz, and then if you critically couple it, at best you can get 5 megahertz. So that's how much you need. Of course, you can live with lower power, but yeah, and also like important to know that it has a B naught power of 4 dependence. In fact, I've done it at a Q band. The DMP it drops from 100 to I don't remember 20 or 30, and of course that's why I don't think you can see at higher fields because of the B naught power 4 dependence.
So what is the highest coupling you would expect to decouple with 10 watts, and how does that compare to the indoor spectrum? This is a question you know. Yeah.
Yeah, the highest coupling I can decouple. So with a 10 watt amp, so as I said, I have like in a critical couple condition, I can get 5 megahertz. So if I can invert the EPR line, 5 megahertz, and then like if I can set, plus I need to be able to saturate then, and then like of course the hyperfine interaction. I would say like for in the case of our DMP, few hundred kilohertz should be easy, and of course I will not worry about the hyperfine coupling. I will perhaps worry more about the GM sensitivity. In fact, I think what would be important is that if you can incorporate an AWG into it and do a frequency churn, I mean, that would even be better. I can maybe expect, not just 80% of frequency, maybe, even higher intensity if I can sweep the microwave. I mean, I'm using just a fixed frequency microwave source now.
Okay. So an anonymous attendee wants to know if more sophisticated sequences can be used for electron decoupling, like TPPM, waltz, etc. Right?
Yeah, maybe, I don't know, but I think like before we move on to such a sophisticated sequence like that, I think like first, the easiest thing to do is to sweep the microwave frequency. I mean, that's what Alexander Barnes did. He used the frequency agile gyrator and show an improvement of 11%, and then like in a factor of 2 in the recent paper. I think that will be first. You need to be able to make sure that you have a strong microwave source, and then you are able to invert invert all the EPR lines, or saturate all the EPR lines first. That will be the first step. Easy steps.
All right. Bjorn has another comment. He says, or another question. He says, do you know why the top DNP frequency profile gives asymmetric enhancements in the experiments?
I do not fully understood what you meant by asymmetric, because I think like I mean, yeah, I can use maybe like 180 or 200 plus minus 10%. What I can say is that I think if you refer to my X10 paper, it's slightly asymmetric because I changed the microwave frequency by fixing the field, and perhaps that would explain why my microwave frequency, because of the probe.
So he says that in the 9 gigahertz profile, you get plus 150 versus minus 200.
Yeah. I do not have a full reason for it, but I think that's because like for the probe that I have had, the microwave power is more intense at one frequency compared to the other one, because like it's the endo probe, it does not have it has a probe, like the Q. Yeah.
Okay. One last anonymous attendee question. Wouldn't self-decoupling effects in electrons be very dominant? And do you see line narrowing at higher concentrations?
I think I think with the T1 of electron, I measure the T1 of electron, which is in the trider is about 2 milliseconds. And then like, of course, sometimes you will rely on the electron to decouple itself, because of the fast T1. But then like at this temperature, the T1 is about 2 milliseconds and trider is known to have a long T1. So I would say like electron decoupling is would help. Of course, at higher temperatures, I'm not sure, and also like maybe for tempo or other bioreactors, like self-decoupling effect would be dominant. But for Trido, for anything with a long T1E, I don't think the self-decoupling will be that dominant. Do you see line narrowing effect at higher concentration? I've not tried that yet. I don't know.
Yeah. So Jeffrey had a comment, another comment. He said that he agreed with Nino and Fred about something. All right, so that's all the questions for today. There were quite a number of them. So let's thank Kong again for a very nice talk, stimulating talk, generated a lot of discussion. And we will be back here in 2 weeks on December 1st. It's not yet completely clear who will be giving talks, but we have several possible candidates. So we will see everyone again on December 1 at 11 a.m. For the biweekly solid state DNP NMR seminar. Thanks again, and we hope to see you in 2 weeks.